Welcome to the dialogue of the International Academy of Information Studies. We are very happy to host our two very distinguished guests, Professor Sara Imari Walker and Carlos Gershenson. My name is Gordana Dodig-Crnkovic and I am a board member of the Academy. It is my distinct pleasure to be moderator of today's dialogue of these two extraordinary, original scientists and thinkers whose work is deeply relevant to information studies. Our today's theme is huge and hugely important for the future of scientific, philosophical, and even cultural development, as it changes the ways we understand ourselves, the nature, the universe, and our place in it. So the topic is information and the emergence of complexity. So let me briefly introduce our speakers. Professor Sara Imari Walker is Deputy Director of Beyond, Center for Fundamental Concepts in Science and Professor at School of Earth and Space Exploration and School of Complex Adaptive Systems at Arizona State University. Her research interests include astrobiology, complex system, physics, among others. And she has written a very exciting new book, Life as No One Knows It, The Physics of Life's Emergence, in 24. And earlier, she co-authored From Matter to Life, Information and Causality with Paul Davies and George Ellis. Professor Carlos Gershenson is Empire Professor of Innovation at State University of New York at Binghamton. He is Editor-in-Chief of Complexity Digest and President of the Complex System Society. He is a member of the Mexican Academy of Sciences and the Mexican Academy of Informatics. His research interests are also many: complexity, AI, artificial life, self-organizing systems, information, evolution, cognition, and philosophy of science. His book includes Complexity 5 Questions, Artificial Society of Intelligent Agents, Design and Control of Self-Organizing Systems, and he has a forthcoming book with Oxford University Press on balance. So something exciting to look forward to. So, and I would add to the list of research fields that Sara and Carlos cover also contemporary natural philosophy, as they are indeed profound and deep thinkers representing our best current understanding of nature and the universe. So I would be very happy if you would accept this invitation to natural philosophy. Okay, and now the format of the dialogue is as follows. Each speaker will give 20 minutes presentation, and we start with Sara and then Carlos. And it is followed by 15 minutes mutual discussion and 30 minutes Q&A session with the audience. So, and the session will be recorded and available on our YouTube channel. So please, Sara, the floor is yours.
Let's see. Okay, perfect. I think I got it now. Can you see my slides?
Yes, right now.
Yes.
Excellent. Okay, I'm so sorry about that. I should have tried it out ahead of time. I don't usually use Google Meet, so it's a little bit alien for me. Thank you for your patience. I was just going to say I'm really excited to be here, and in particular for the conversation. I'm looking forward to Carlos's talk as well. What I wanted to focus on today was actually the concept of measurement of the concepts that we associate with information and the emergence of complexity. And the reason for that being that I think a lot of us, particularly in this community, have a sense that the biosphere has generated a lot of complex structures, and that when we think about complexity in information, there's something very fundamental and deep there. And we obviously can see a lot of living forms in our environment. And in some sense, the problem of the origin of life, which has driven most of my career, is trying to actually figure out how do we actually quantify the transition from the inanimate to animate, where the animate is typically associated with information and complexity in the way that we see it in the environment around us, but we have yet to observe on another planet. And so I wanted to start the talk by saying that the origin of life traditionally as a research field has been studied as a historical problem that happens in chemistry, but the phenomena of the origin of life might actually be a much more general phenomena. And so for the stance that I'm taking in this talk, the way that I think about it is the universe can generate combinatorial spaces, but it can't search the full space. If you think about chemistry and all possible molecules, it's not possible for the universe to erratically explore all possible molecules, as few have been arguing for decades. And so a transition has to happen, what we call the origin of life, where selection and specific constructive circumstances take over. But we don't just see that happening in chemistry, we see that happening across diverse substrates, from minerals to planetary atmospheres to languages to what's happening in algorithms in our computers right now. So I think very much what's emerging right now across a lot of disciplines is that the thing that we call life or intelligence might be an emergent process that's happening across diverse substrates. And so what I'm really trying to think about right now is how do we formalize measuring that process so we can actually build a new theoretical physics associated to a metrology that actually has some physical grounding. And so I think, one of the key questions here is whether the study of the science of complexity and information generally is a subjective science or an objective science. And I think historically it's been very subjective, in part because most of the measures of information and complexity we have come from computer science, where one has to actually define a reference machine or a language or labeling scheme with respect to talking about the complexity of an object. So it's very descriptive rather than an objective feature of the physical structure that we see in the world. And that actually works for a lot of problems. But if you're developing a fundamental physics, I think that we need to transition to a more objective way of thinking about complexity in the universe. And I'm happy to talk about the subtleties of this distinction. This is more of a provocation. I think it's actually really quite deep about why computation can't be a fundamental description of nature. So I just wanted to sort of preface this by saying that the history of metrology is very deep. It's as deep as science itself. And most of our scientific advancements have been driven by developing new techniques of measurement. And so one of my favorite examples is beautifully written about in this book called Inventing Temperature, which is the process of inventing the concept of temperature. And there's a lot of really amazing things about metrology generally and how it takes decades or even centuries to come up with standardized measurement schemes. And I think for complexity, we don't have any kind of standardization where we can compare across systems. But what happened with the innovation of temperature is temperature also was likewise very subjective, very measurement device specific, until we actually came up with a theoretical abstraction, which is the concept of absolute zero, which is a quantity defined by the absence of heat. It's not one that is actually physically realizable, but it is something that allows us to reference all other heat objects that contain heat with respect to a temperature scale. And so this was actually really critical to the development of statistical physics and thermodynamics. You'll see similar things in the history of science when you look at the speed of light being absolute and objective with respect to different reference frames. And so one of the things I've been thinking about a lot is if we're thinking about a science of complexity, what would be the objective reference scale from which we could talk about complexity and its emergence in the universe? So most of the last several years of my work have been in part focused on developing a metrology of complexity. And what I want to say about this is that the reason I think this is critically important is not because I'm obsessed with the science of measurement, although I kind of am at this stage, but because when you think really deeply about the nature of our abstractions and how they're embedded in the physical world, and you try to make that correspondence as tight as possible, it actually allows us to do new things in building theories. And so I'm going to talk a lot about our development of assembly theory from this perspective, but the major innovation of assembly theory is really to take the concepts of information, causation, and complexity and make them grounded in a science of metrology so that we can build a theoretical physics from them. And so this is a really different approach to the science of complexity than we've had traditionally, but I think it actually will provide a lot of new insights into how we can think about the nature of reality and what life is more fundamentally than we have been able to in the past. And so obviously, like, the questions we're asking are quite old. So I have a little picture here of Paley's famous watch and this question of design in nature. And evolutionary theory explains some features of design in nature. That was, the whole revolution of the middle of the 1800s with Darwin and contemporaries that is ongoing today. But of course, we still don't have solutions for the origin of evolutionary processes. Where did they come from in the first place? And as I was saying at the beginning, if we're thinking about just sort of mechanisms of the universe as a self-constructing system in a combinatorial space, you need to actually have a mechanism for the emergence of evolutionary processes. And so we really think about that as a mechanism of selection and how the possibility space gets constructed in the first place. So really, to take the sort of argument of design in nature, and really what you're asking is, how does the universe build information to specify the existence of certain objects? It's much easier to think about that in molecules than any other physical system. The reason being that we know enough about chemistry, and the scale of atoms is sufficiently small that we can actually, like, computationally talk about the space. And so here I'm just showing molecule taxol, which is one of billions of possible molecules with the same molecular formula, just to show that the combinatorial space of chemistry is so large that we should not expect the universe to ever make every possible molecule. And in fact, in assembly theory, we define a precise threshold. Is it possible for someone that has a mic on to put their mic? I can hear some background noise. I don't know if other people can hear me. It's not too loud for other people. Okay, I'll keep going. All right.
Can we listen to you?
Yeah, you can hear me? Okay, good. I wasn't sure because it was quite loud in the background for me. So this point about, the size of the space, I think many of us have talked about it and thought about it. And so I really take this issue of the size of the space seriously as a physical limitation, not just a computational limitation. And so when I look at a space of possibilities like this, I really think about it as an imagined space that I can actually create as a human that has a certain level of intelligence evolved over billions of years. But the universe outside of structures like me doesn't have knowledge of this space because it hasn't generated them. And the idea of ergodic sampling is impossible because the universe actually has to construct itself, and it has finite time and finite resources. And so the question is, how can we actually measure how much selection and evolution is necessary to get to any of these structures, recognizing that we won't be able to achieve all possible structures? And so, so for the purposes of the discussion today, and just to keep things as simple as possible, I want to try to make a distinction between objects that are spontaneous or selected. And spontaneous objects, I would say, have a constructed complexity or are simple enough that they can actually form readily anywhere conditions are favorable. But selected objects would be things like the ribosome, which is obviously a reliable feature of the sort of constructed complexity on our planet, but that's because we actually have a physical object, the cell, which reliably generates ribosomes repeatedly. So it's a causal regularity of our planet, but it's not a causal regularity universally, and we don't expect ribosomes necessarily to emerge on other planets. In fact, I think it's very unlikely that the exact same molecular structures will appear on other planets because the space is so large. And so there is sort of a physical boundary between things that we think can universally happen, say globally anywhere in the Hubble volume, and things that are very specific to selected histories that might emerge on a planet. And I'm really interested in those particular selected histories because those are the things that we actually want to qualify as being life. And so in assembly theory, we are trying to build a formalism around this set of ideas, and the formalism is deeply tied to the metrology of how we think about actually going in the lab and testing them. So in part of our research program is actually to demonstrate that contingency is a real physical feature of objects, and that we need to really radically reframe some of our fundamental theories of physics to actually treat that as a fundamental property. So causation is fundamental. Contingency is fundamental. And the reason for doing this is that if you think about the space of possible objects, when you actually adopt contingency and causation as fundamental properties of the physics, you can build a space, which we call the assembly space, that's expanding with the complexity of objects and allows defining a boundary where beyond this particular boundary in a substrate specifically defined assembly space, objects can only exist if there is a selective history that can actually specifically construct them. So you can imagine if you think about constructors in the sense of von Neumann constructors, or you think about causal histories or lineages in biology, basically what we're saying is that there are some objects that can never exist unless they have a lineage or a set of stacked history of causal constructors behind them. And I don't really, different people want to use different language for it. I'm really just more interested in getting at the fundamental concepts. So I think all of those sort of concepts of information complexity and causation are kind of wrapped into like what we're trying to do to try to just get at like what is the fundamental structure. And one other point I want to make about this is there is an ontology that we assume where objects can only exist if the parts to them already exist. So we actually are assuming an ontological ordering to the existence of objects. And that's a fundamental feature of assembly theory in the way that we talk about the space of possibilities. So in some sense, when I make this distinction between spontaneous and selected, I'm actually making a stronger statement, which is things that are selected are not possible to form spontaneously because they have to have a causal ordering to the structures that need to precede them. And the way that we talk about that causal ordering is through a feature of assembly theory we call the assembly space. This is an assembly space for a particular molecule. The definition of the assembly index is the minimum recursive causal joining steps necessary to generate the objects. So basically, if you think about a molecule, you have a physical object that we actually observe that our universe created. And we say you can basically take that molecule apart and you can look at all of the ways that you could possibly create that molecule by doing physically allowed operations of making bonds. And then we look for the minimal such structure. And it's actually not so important what the features on that graph are. What really matters is the minimum number of steps, because that's an invariant physical feature of the object. And this is one of the reasons that we think about the assembly index as an intensive feature of a molecule. And it's also intensive because it's something that we measure as a feature of the molecule, and it doesn't depend on the context or environment or any of the properties of system size or things that it's always a feature of the molecule, just like other properties in the molecule. And so because we are developing a metrology associated with the assembly index, I think about the assembly index really as a physical feature, and it has a lot of the features that we assign to material objects in the history of physics. One of them being that it's actually an invariant intrinsic physical property. And because we think of this causal structure as actually a feature of the molecule, there's an interpretation of assembly theory, which I rather like from the philosophical perspective, where you can start thinking about matter as informational. And in some sense, objects that carry more information in them actually are just deeper causal stacks as far as the recursive history necessary to construct them or necessary for that object to exist at all in our universe. And it's in this sense that we talk about causation being a material property. So assembly index measures causation. A feature of contingency is also important. So I mentioned that objects require specific histories in order to exist. And so the way that we look at that is we look at the observed objects we have in our environment, we deconstruct them to try to look at the causal rules that are actually intrinsic to the object as far as their recursive construction. And when we actually count how many of indistinguishable objects we have in our environment with respect to a specific measurement scheme, we can define a copy number. And the copy number, in some sense, is actually an evidence of the contingency. And I really want to make clear, because I think there's some distinctions to be made about this, that the assembly space, when we deconstruct it this way, the objects that exist actually are what reveals the fact that there could have been other objects. So this whole idea of counterfactuals related to causation or counterfactuals related to selection and informational properties, I think is an artifact of the space that's physically real, which is, in my view, the assembly space, and that we can actually deconstruct that space and then look at alternative histories that could have been possible. And in assembly theory, we talk about that space in a few different ways, which I'm not going to go through in a lot of detail just in the interest of time, but I'm happy to talk about them in the discussion. The one that I'm interested in for purposes of discussion today is just this assembly contingent, which is the idea that within the space of all possible objects, the only ones assembly theory would conjecture are the physically real, the kinds of configurations of objects that we can observe are ones that actually have co-constructed histories that allow those objects to be selected together. And so there's certain properties of recursion and redundancy and modularity that we see in biology that obviously emerge out of this, as well as other theories of complexity, And the assembly observed that we see is one such history. So I think this part is really important, that when we think about the space of all possible contingent histories, they are getting exponentially larger as we move into the space of possibilities, which means you need more and more selection to actually move through this physical space. And the structures that we observe carry all of the contingent history within them and also allow for some constraints on the future of what can be constructed. But there is, room for novelty and open-endedness. So not everything we can imagine can exist is one point of sort of making this layered space of assembly theory, because I think there's been a sort of tendency, particularly in fundamental physics, of assuming all of the imagined possibilities that we could have are actually equally physically real. And I am, I guess I'm about as much of a materialist as you can get. So I really just think the universe exists as it is with the objects in it, but that we maybe don't have as good a definitions of some of the material properties. And I just want to make a point about copy number, because the copy number is not the same as a frequentist interpretation about probability. So someone might say, I count objects in my environment, and this tells me something about the likelihood of their formation. But I think that we actually can't a priori say anything about the likelihood of formation of objects, because there is no forward process, no universal laws that tell the universe what new kinds of causes will emerge along a particular trajectory. So copy number in assembly theory is really just an indication of the existence of a causal mechanism that allows that object to exist at all. It doesn't say anything about the probability of that object within the space of all possible probabilities, which I think is an over extrapolation of some current theories. And so after defining causation and contingency, we can define selection within the space, which we do using the assembly equation, which is the two features that are important are exponential in the amount of causation in the objects and linear in copy number. And this has some really interesting properties. It allows a natural bound to the abiotic complexity of objects. And if you see an assembly larger than that, it indicates a selective mechanism that we would associate with life or a long lineage of causal processes that have specifically constructed a set of objects. The two key features, though, for the purposes of metrology, which I'm going to spend the last few minutes on, are the assembly index and copy number. And this allows us to really think about how to measure life in diverse substrates. And so I'm just going to talk about two in my last couple minutes. The first one is molecules, which are a little bit more familiar for anyone that's read our work on assembly theory, because this is published literature. And for molecules, objects are just molecules, right? Like we can count molecules, we can detect them as distinguishable objects. So we have, some objects, some forms that exist in the world. We can label them as this is ATP, this is ATP, this is ATP, and we can count them. So molecules in some sense are really easy from an assembly theoretic perspective, because the causal bounded unit is actually a thing that we can count in the environment already. And for purposes of measurement, we use several different techniques. We use NMR, infrared spectroscopy, and mass spectroscopy. I won't talk about those techniques in this talk, but there's some published literature on that. And most of these instruments already require a really high abundance of these molecules. So in some sense, these molecules are already selected to exist before we even get them to the measuring device. An assembly index in this context is just the causal decomposition of the molecules via fragmentation, which gives a shortest path like the one I showed for adenosine earlier. And we had a result published a few years ago where we actually looked at measuring molecular assembly index for a variety of different molecules using mass spectrometry. And what we found is above assembly index 15, you only find molecules that were constructed by a living process, which was confirming some of our predictions from assembly theory. And some of the things that we've been developing subsequent to this are that this sort of boundary is actually predictable. There are abiotic bounds on any combinatorial causal space. And so I expect a threshold to be a feature of any assembly space, no matter what the substrate is. And so just to give an example, I'm going to talk about atmospheres. Briefly in the same context as molecules. So just like a molecule, an atmosphere is an object that we observe in the universe. So you imagine a planet and you have a distinguishable unit, which is an entire planet. And you can measure planetary atmospheres as an aggregate using infrared spectroscopy. This is exactly what we do for exoplanets. The copy number here is the volatile gases that are abundant enough to actually contribute to the atmospheric signature. So Earth's atmosphere has a diversity of gases that you would never be able to detect remotely because they actually don't contribute to the infrared spectra that our planet generates. So those wouldn't actually be counted as part of the feature of the atmosphere in assembly theory. And the assembly index, because the sort of point of contact for measurement of a distinguishable causal object is an entire planet, we treat the atmosphere, even though it's a collection of atoms and molecules in the same sense as molecular assembly, the properties of atmospheric physics and chemistry are radically different. And so we treat the assembly index as the causal decomposition of the entire atmosphere composition. And when you do that, you can measure life in atmospheres in the same way that we measure life in molecules. And so this is just some early results. We're trying to finish this paper right now, basically just showing that the predicted values of the assembly index versus the actual values we might extract from infrared spectra yield an ability to measure directly from atmospheric spectra, not knowing the identity of the molecules, the assembly index for that particular spectral pattern, which means that basically we can read out directly from the infrared the causal depth of the atmosphere from an assembly theoretic perspective. And if we measure the assembly index of the atmosphere here labeled as joint assembly index, we can do this for all the different atmospheres that we know, including some hypothetical planetary classes that exoplanet researchers study. The color here is just indicating differences in temperature. And the main feature is that Earth's biosphere and technosphere are much more complex. And naively, you might think that this is because we have a much higher resolution of the atmosphere of Earth. But what we've done here, because of the copy number constraints in assembly theory, we've actually had to do a careful analysis of like what would be sort of a uniform copy number threshold across planets, and actually looking at the causal structure for things that are abundant and only things that are abundant. And so this would be things that were very evident of selection. And then these are just some of the assembly spaces for different atmospheres that we've generated. So just to conclude, we're trying to look at this across very different substrates and basically say that, we can detect life in different systems. And the main goal is to develop a standardized scale metrology of complexity that will allow us to detect life in any substrate. And the features of assembly theory that are really important is the structure of the assembly space is very substrate specific. And so it's not like, so you can have a universal general theory for detecting life in any substrate, but the causal mechanisms have to be dependent on the substrate. And I think this is actually one of the reasons that we observe substrates to have different properties in our physical environment, is because the causal mechanisms are trapped in substrates in different ways. And so far we've applied the theory in molecules, minerals, which allows you to detect technosignatures and minerals. I didn't have time to talk about that one today, in atmospheres, but we're expanding to test in diverse substrates. And there are a lot of theoretical predictions we're making and experimental validation that we're working on. So with that, I want to thank everyone, and I'm looking forward to the discussion. Thank you.
Thank you very much, Sara. We will proceed to Carlos, and we will have discussion between two of you after Carlos' presentation. So thank you so much.
Thank you, everyone, for being here. I'll present some ideas that in some sense are aligned with what Sara presented, and in some others they might be conflicting, so it will be interesting to see what comes out of it. So, we can ask ourselves, what is reality? And then we can spend the rest of the hour not reaching any conclusion, because of course there are many approaches to defining reality. One approach would be to say that what physics studies is real, matter and energy, but then where does that leave information? And then whether information is real or not, some people might debate, but I guess that we can say that information has causal influence in matter and energy. So for example, money, the value of money is not defined by its physical substrate. Of course, it requires a physical substrate, but let's say if we look at the molecules of a gold bar or shells or cacao seeds or whatever might have values, or some bills, we won't be able to define how much value people give. And money is required to transform matter to make buildings and cars and planes and so on. So, I mean, it's clear that money as a social construct has a causal influence on physics, matter and energy. So we could say that information is as real as matter and energy simply because it has a causal influence on them, independently on what's reality. And in philosophy, epistemology studies how we get to know things. How can we know? How do we know? And of course, we would like to know as much as possible, but we are limited in our primitive brains. And as Sara mentioned, we would like to be as objective as possible, but we are limited because in order to know anything or to describe anything, we do it from a subjective perspective. We cannot speak about anything if it's not from a subjective perspective. So we don't have a direct access to reality, whatever that might be. And an example I give already for quite some time. Imagine we have a sphere and it's half white and half black, but actually we just perceive one perspective, so we don't perceive a sphere but a circle. And then depending on our perspective, we will see a circle of different colors. So if we ask different people, oh, what's the color of the circle? We could say, some people would say black, some white, some half. And we could go to holy wars trying to convince each other what's the real color of the circle, or make some democratic mathematics and just take the average, but probably the observers will not be homogeneously distributed, so probably we won't get the real color of the sphere simply because we don't know what's the distribution of the observers, and so on. And this just to suggest that there's no single description of any phenomena, therefore no single truth. And I mean, this has some implications in philosophy, but let's say we can be pragmatic and just try to follow what's useful, what works. And of course, different descriptions might be useful in different contexts. So we can say that more than one description might be suitable for the same phenomena. And let's say the objective part of phenomena is studied by ontology, which is the part of philosophy that tries to study how things are independently of observers. However, as I mentioned, in order just to speak about ontology, well, things themselves, we're using language, and that's already a simplification, and that's already subjective. But at the same time, epistemology also needs an ontology, because otherwise we could come up with arbitrary descriptions of phenomena. So, I mean, this suggests that they cannot be really separated. I mean, this is not new. I like this quote from Schrödinger. The world is given to me only once, not one existing and one perceived. Subject and object are only one. The barrier between them cannot be said to have broken down as a result of recent experience in the physical sciences, for this barrier does not exist. In the sense that this distinction between object and object at the same time, it's also artificial. And in Eastern philosophies, including Buddhist philosophy, it's understood that this is an arbitrary distinction, and we cannot really separate between subject, object, and action of perception. So this started years ago, more than 20 years ago, when I was reading investigations by Stuart, who is happily here. So Stu posed in his book precisely the question of how to describe information in terms of matter and energy. And what I thought was that instead of trying to do that, which is not feasible, we can do the opposite. We can try to describe physics in terms of information. So if since physics it's something we can describe, then if we can describe it, it's also information. So then we can generate tentative laws from first principles that apply not only to matter and energy, but also to information. So very general notion, we can say that information is anything that an agent can perceive or sense. And we can say that an agent is a description of an entity that acts on its environment. The meaning of information will be given by its use that the agent gives, and computation can be seen as transformation of information. An important aspect is that information is not necessarily conserved as matter as energy and energy. So that gives some flexibility. And most people would agree that there has been an increase on complexity since the Big Bang. How this complexity has increased, how to measure it and so on, that's a different question, but we can use this arrow of complexity to identify general principles of information. So there are these 8 tentative laws of information, and laws between brackets, because they could also be seen as tautologies in the sense that they are so obvious that it's not, I mean, they're almost defined to be like that, but then they can be useful in different ways. So the law of information transformation tells us that there is change in the world. And because of that, information will potentially be transformed as different agents perceive and interact with it. And this gives us variety and novelty. So it's basically like random variation in natural selection. That's one instance of information transformation. And then information can change, or an agent perceiving that information can change. So actually the information doesn't change, but the interpretation or the meaning of the information can change. An agent can actively change information externally, and then there can be stigmergic change of information. You can say that information propagates as fast as possible because there will be, from the variety of information that is produced by transformation, there will be some information that will be fitter to propagate than others. And again, this is a tautology because we define the fitness of information precisely on how successful that information is for propagating itself. And this will generalize natural selection, the maximum entropy production principle, the second law of thermodynamics, and Kaufman's tentative fourth law of thermodynamics. And there are different types of information propagation. It can be autonomous, symbiotic, parasitic, altruistic, depending on, let's say, who is propagating which information. Law of requisite complexity, it's a generalization of Ive's law of requisite variety. And it says that more complex information will require more complex agents to perceive, act on, and propagate it. So you can explain the arrow of complexity in evolution as a drift, in the sense that if by variation there will be some information with a higher complexity, then that opens up a niche, and then agents will require to have also a higher complexity in order to exploit that information. The criticality of information, this expanded in my upcoming book about balance, and has also been explored by many people. Basically, the balance between order and chaos that is required for evolution, computation, life. And let's say if information and its change is, let's say, relatively slow, then you have order, but then you cannot adapt. And if it's too high, you have chaos and you can adapt, but then you cannot maintain and propagate information that you had already. So this naturally tends to this critical balance. And also from Stu's investigations, he proposes the idea of constraints in thermodynamic systems as organization. And we see that information produces constraints, basically the organization that regulates its own production. So we can say that information has a certain control over its environment. The information potentiality says that agent can give different potential meanings to information. So we can have polysemy. Same information can have different meanings, but also different information can acquire the same meaning, homonymy, and this is related to passive information transformation. And finally, different agents in different contexts at different levels of details can perceive the same information in different ways. But then this gives always space for novelty and limits prediction in an inherent way, in the sense that if different agents can perceive the same phenomena, the same information, and give it a different meaning, then you cannot specify what will the meaning of information be. And if we consider different scales at which information can be perceived, we will see that if we go at lower scales, then we include more detail, and that requires more information to describe what's happening at the lower scale. And then information will tend to infinite. And even if it's not infinite, in practice, we will have unique states that will never be repeated. And this limits predictability in many ways, because let's say if every state is new that the system visits, then how can we say anything about that? Of course, when we eliminate distinctions, we reduce information, we increase the scales of observation, we will find regularities, and then we can start to generalize and speak about regularities in phenomena, and prediction becomes feasible. And then when the scale tends to infinite, then information tends to zero, because everything is included, there is no difference. And this is related to the highest view in Buddhist philosophy. There's no right or wrong, because everything is there already, something all-encompassing, and the experience of this is described as bliss. So following the law of information criticality, we can say that agents will tend to balance of scales, trying to predict most with the least information. Because of course we can ask, okay, between these two extremes of scales, which one is the most useful? And just to apply these ideas to a couple of concepts, we can also describe life in terms of information, and measure or so-called life ratio is simply the ratio of information produced by itself over the ratio of that information produced by its environment. And that reflects at the same time autonomy, individuality, and also suggests that life is something to be expected in the universe, because we have increased complexity, increased control of information over its own production. So at some point, you would expect that information will have more control over its own production than the environment producing that information. So of course, this can be measured, and also related to cognition, intelligence, consciousness. We can say that system is cognitive if it knows something. So then all agents will be cognitive because they know how to act in their environment. And then we can speak about different levels of sophistication, different levels of, let's say, of complexity of agents. But there would be no boundary between non-cognitive agents and cognitive agents, because all agents would be cognitive. And the same would be for intelligence, for consciousness. That, let's say, integrated information theory, it's one of several current approaches to study consciousness, which is also based on information. And let's say this view would fall into panpsychism, because there's no clear way of drawing the boundary between what would be cognitive and what would not be cognitive, what would not be intelligent and what would be intelligent, to just different levels of sophistications. Okay, so everything I said, it's description, so it's epistemology. So what can we say about ontology? what information really is. And again, we cannot speak completely objectively about information or about agents, so it has to be partially subjective. But again, we need an ontological basis for epistemology. We cannot separate this. And of course, this is related to limits of science, to limits of philosophy, to limits of language, and that would be like another talk. But now, let me just share some of recent questions and ideas that are still in process of development. So some time ago, I was just speaking with my youngest daughter, and I just posed to her the question, oh, can you imagine the set of all possible languages? I mean, as a very large infinite set, because of course, it's not only all possible strings or not only possible combinations of symbols, which is a very large infinite set, but all possible combinations of all possible strings and all possible meanings. So let's say, of course, that's a very large set, but then all truths should be in there somewhere, and then how to find them, that's a different question. But let's say we can speak about that idea. And then this is similar to the concept of the Rulliad that Stephen Wolfram has been developing recently, which is the set of all possible computational programs in the computational universe. And according to Stephen, I spoke with him about this, and for him, this Rulliad would be the real thing, let's say the ontology. But it's quite inaccessible for us. We can just explore tiny slices, which is, let's say, the few programs that actually we can explore, because we can state, okay, this Rulliad is the state of all possible programs, but we cannot start enumerating all those possible programs. Well, maybe we can, but let's say we cannot list them fully. I mean, the same happens with numbers. And then another topic that we have also discussed with Stu is this idea of res potentia and res extensa. So we could see this Rulliad, or let's say set of all possible languages, as a res potentia, in the sense that that's possibilities. But actually, we need something to instantiate it, to make it res extensa. And that's computing or information processing. And then we could ask whether each of those res potentia and res extensa are real, because it would be like the Rulliad, it's equivalent or similar to Platonic ideas, that ideas exist already and then we just kind of instantiate them. And then there's this question whether mathematics is discovered or invented. And it's related, but I mean, I think in practice it doesn't really matter. But what is relevant is that I think we can say that most of all possible information is not computable. So just like Sara mentioned, that let's say there's this space of all possible assemblies, but the universe just instantiates a very limited subset of those. I mean, like, considering all possible chemical reactions, just a tiny fraction will ever occur in our universe. And then, of course, that gives a strong contingency. But then it's interesting also that within that very tiny space, we have such richness of dynamics. So in principle, we can infer something from that tiny space about all possible chemical reactions. But then we could say that because of that, let's say following the same idea in terms of computation, that most information is not computable. So if we start from physics, we cannot compute concepts such as love or God, which have a causal influence in matter and energy. So this would mean that you cannot describe these concepts of love or God in terms of physics. Not because if you have like the full description in terms of physics of the whole universe, let's say, then you might reach some description, but it's simply because it's not computable in practice. And just to conclude, a few weeks ago, I was in Tokyo at the Musashino University giving a talk about Buddhism and philosophy, and a retired professor, Rovendesho Murashi, asked me at the end, like, okay, who are you? so who am I? And then I say, well, I am information at a relative level, but let's say my true essence is not separate from anything else because everything is included. Okay, so with that, I stop.
Thank you very much to both Sara and Carlos. Fantastic, amazing. Now it's time for a dialogue between two of you. So it will be really exciting to see. Please, the floor is yours.
Excellent. I don't know where to start. That was amazing, Carlos. Thank you so much. I guess maybe we could talk a little bit about epistemology and ontology, and also, the space. I'm really interested in this idea of the set of all possible languages and making an ontological commitment to it, because that's a leap I can't take, and I see a lot of people taking it, and I don't understand where the sort of justification for assuming things that are imagined are physically real outside of the bounds of our imagination. So maybe you can explain a little bit more about why you feel comfortable with that ontology.
Yeah, I wouldn't say that let's say the set of all possible languages is real, or the Rulyard, as Wolfram defines it, is real. He would say that's the real thing, like that's ontology. I'm not sure whether I would agree, because I mentioned that it might be that is real, and then the instantiations are just like, you could say, like epiphenomena or like shadows in Plato's cave. And then the real thing, it's like this infinite set to which we don't really have access. But we could also take the opposite stance. That's okay. That's an abstraction, and since you cannot start enumerating and it's infinite, then let's say you cannot touch it, you cannot grasp it. Then it's just your imagination. And if we want to be pragmatic, we need to work with things that we can not only speak about, but also manipulate and define better and observe and analyze. And in that sense, just the instantiations we have would be real. But I mean, for example, in Buddhist philosophy, definition of reality is something that doesn't change. And then, of course, ego is not real because we are changing constantly. And let's say planets are not real because the mountains are. And then what is real is the potential, which would be, let's say, in the context we're speaking, would be the potential of information to acquire any arbitrary meaning. And then that would be real in Buddhist philosophy. But I mean, taking this idea that we can describe the same phenomena from different perspectives, we can also describe reality from different perspectives. So from one perspective, then the Rulyard would be real, and from another, it wouldn't be real. And instead of saying this one is right and this one is wrong, for me, it's more comfortable to put on the table, okay, there are all these options. And in some cases, it's more useful to use this one. And in some other, it's more useful to use this one. And then let's just agree which one we are using at a given moment, not to get confused.
Yeah. Okay. I have two more questions, if I'm permitted. The first one is just a follow-on to that, because I think, in my mind, there should be an empirical distinction between the two perspectives, right? And so in some sense, I feel like this is part of the program of trying to make information a physical quantity, is to decide whether the space of all possible forms is a real thing out there, or we're physically limited by what the universe has created in the past. And so I see opportunity for a real physics of contingency and information, where you can actually do quantitative tests in the laboratory of that, but you have to assume an ontology, obviously, to do that, which any theory has, as an assumption. So, so I just wanted to comment on that, but a corollary to that, which I also have thought a lot about, and I'm really curious about your perspective on, is the concept that information itself is not material. Because I used to think it was like an abstract quantity, and it certainly is an abstract quantity. But if you look at the history of physics, mass, energy, temperature, all the things that we think of as material properties are also abstractions. And there's a certain process we do to try to talk about abstractions as being physically real, which is the process I think science is doing. And so I don't make a distinction between information and physical material, except that I would say that information is something that we haven't regularized to really understand what the sort of universal regularity we would be talking about, that we could talk about as a material property. And probably that's just because we don't have enough history to actually do that yet. So I'm curious if you think it could become a material concept, or you really think this immateriality of it. Sorry, that was a long-winded way to get my question, but yeah.
No, I think that if we agree on a particular substrate, then we do speak about information, and like with computers, let's say random access memory, then you say, okay, how many kilobytes you have or whatever, and it's very precisely measured, and nobody has any problem. The thing is that with information, you can have multiple interpretations, and the same information can acquire different meanings. So it's not like, it's like having different rulers, and then you don't know which ruler you will use beforehand. And the thing is that if we try to say, okay, only the instantiations of, let's say, chemical reactions or materials that have occurred will be real, it will always be in construction, because, for example, there are all these atomic elements that occur in our universe just because there's an advanced civilization that produced them. And the same for many molecules, and it will be something that we would need to constantly update. And it seems to me that, in a way, this is also related to limitations of formal systems, as, let's say, in sense of Gödel and Turing, the completeness, consistency, non-determinism, because for most of physical properties where we have conservation, let's say in matter and energy, then consistency is kind of easily applicable. But then in information where you don't have conservation, and then you can change arbitrarily the rules of the game, consistency is not always, not only possible, but even desirable, because if you cannot change the rules, you cannot have evolution, you cannot have creativity. So, predicting novelty, it's a oxymoron, because the moment you can predict it, it's no longer. So if you reach a configuration of the physical world where you can predict everything, then evolution stops. So in order to go beyond that, you need information that will be flexible enough to change its meaning, and it will be like changing the rules of the game. And at the end, I would say that physics and information are simply different descriptions of phenomena, and it's not that physics is telling us about reality and then information is just telling about our subjective experience. I think they're both narratives, and they are useful in their own way, and we should use both, not to say, oh, this one is good, this one is bad, and then just try to shift from one to the other. And I was wondering, Sara, you mentioned that computation cannot be a fundamental description of nature. Would you please expand on that?
Yeah, I guess it's to your point about different levels of description. So I think I should qualify what I mean when I say theory is objective, because I also share the view that all theories are abstractions that exist in human minds, and none of them are objectively real in the sense that like we have any access to the real world. But I still think science works, and we can talk about objective features about reality. And so I think there's a really interesting tension there. But when I'm talking about objective properties, I mean with respect to the content of the theory, this is something that you can validate across different substrates, and you have a sense in the theoretical abstraction that this is an invariant quantity. So like the speed of light is a great example, right? Like we have an assumption that the speed of light is invariant to reference frame.
Yes.
It's observer independent, it's measurement scheme independent, right? And that's statement of the theory, and that statement of the theory allows us to test the implications of that idea in the physical world, and that's basically what we do. So when I say that theories have that kind of objective content, I'm thinking of some property of the physical world that we assume, you know, we can use as an abstraction that we reference all physical objects to.
Yes.
And
Yes,
the theory of computation doesn't have that. That's at least observable in the sense that the only things that we talk about that have that property might be like Gordana complexity, but that exists at an infinite horizon. And, you know, we have to actually have a constant that we actually also don't know, which, you know, tells us the value between different machines. And if you look at it for small machines, it doesn't have an absolute hierarchy or objective sort of ontology to it. So I think that the theory of computation exists in the same space as concepts of space and clock time, that it's relative to an observer, a reference machine, or measuring device. And that there is a sort of an objective ontology, which is what we're trying to develop with assembly theory, that would be about the actual causal structure, because if you have to assume an ontology where there is an ordering to existence. And so obviously that's an assumption of the theory and a property of the abstraction, but if you embed that in the physical world, then you have sort of a better way of talking about it. So I think of computation as sort of the reference frame dependent measurement, and the ontology of causation as being the more objective thing in the space of theories in thinking about information.
Yes, so I think this ties precisely with what I was saying, that information and also complexity are not invariant.
Yeah.
For better and for worse. So of course, for worse because it's not objective, and then you don't have like a shared frame of reference. But for better because then you have creativity and novelty and evolution.
Yeah, I guess I don't think the physics excludes it though, right? So I think the universe is really not deterministic, right? And I actually, my sort of ontological perspective on things. So I take firm ontologies, but I know that the ontologies are, you know, like a tool for building theories, and whether or not I'm making objective statements about the world, you know, I have to assume an ontology, and then I have to subject it to experimental tests. So the ontology I assume right now is the future is not predictable. And in Stu's language, it's not pre-statable. So I completely agree with that. And that's where novelty comes from. So, you know, like the idea of the construction process and all of these things, they're all features of the past. And I think one of the issues we have is we take this dynamical systems view of reality, which is inherited from Newton, where we have an initial condition that we assume is real, and we can run a law of motion forward, which we also assume is real. But really what we have is the objects of our experience in our immediate environment that we might be able to deconstruct and actually learn some rules about in the span of a human lifetime. And then we can sort of infer something about the space possibilities we live in. And the laws are one sort of regularity we've extracted from that space, but the laws of physics as we talk about them now are deterministically closed, and we keep seeing an open future. So I think it's epistemologically confusing for us. So I just want to clarify that like an ontology where you assume that there is something objective doesn't mean that the future can't be open. It just means that the objective features are about the past. And I think the theory of computation also has this property, but we tend to think, because we think in a linear time where we go forward, the theory of computation says you can't compute this thing in the future. It already knows that like that future horizon isn't, but once you compute something, you can say something about the computation that created it. So it also has an arrow of time in the same sense. So I think there's some really interesting features of that, but yeah, so I just wanted to clarify that point, because the word is confusing.
You have mentioned several times about causation, and recently I've been thinking that it's not only problematic to try to find some objective basis of causation, but even a subjective basis of causation seems problematic. So,
Well,
I
I think,
mean, it's not that I have a solution or anything. It's
yeah,
just to me that even when we depend strongly on the concept of causation, I find it very problematic, precisely because it's very difficult to not only define, but to identify and to agree. And yeah.
yeah. So, I mean, I agree with you. I don't like counterfactual statements because I don't like this idea of iterating over things that we actually can't, fully intervene on a system. So these feel physically unreal to me. So, the way that I've approached these questions is starting from thinking information and causation are somehow fundamental to life and define the transition of life, to recognizing that the words we use are radically imprecise. So even if I could, iterate over the space of all possible languages, I don't think that's very helpful because every language will be imprecise to reality. So I kind of have tried to take a perspective where I want to understand the phenomena of the transition to life. And then the definitions of these concepts come from trying to formalize that transition in a way that we can actually test it. And so for me, causation comes from the theory, not from prior conceptions of what causation is, although they obviously inform it. And in assembly theory, causation is just the minimum amount of steps for an object to exist. That's just it. And for different substrates, it'll be different. And it's self-consistent within the context of theory, but it might not, conform to other people's definitions of causation. But the point is, it's a kind of causation that you can measure as a material property, which is a feature that I'm interested in as a physicist. So I think there's some interesting. I guess the point I have that I'm deeply interested in is I think there's a lot of philosophical concepts that are very interesting when you start to try to build a theoretical physics out of them. And the whole process of theoretical physics has been really interesting to me as an intellectual exercise over the last few hundred years, because when we do that, we end up building entirely new philosophies about things that we thought we understood pretty well before. And they may or may not be better grounded, but I think they have, it's interesting to try to build your philosophy by this iteration with empirical measurement and experimentation. And so I try to let this feature of the chemical universe or, the universal languages and things inform, development of the theory. But I'm pretty agnostic about how reality actually works.
One of the things I like.
Yeah.
One of the things I like about assembly theory is that it's very pragmatic, so you can calculate not only chemical molecules, but let's say manufactured products in an economy and so on. But I was wondering whether you have thought how easy it might be to generalize to, let's say, more abstract complex systems, like what might be the assembly index of a democracy or a blockbuster or...
Yeah. I have thought about it. I think it's very challenging because those systems are so large in causation and time that it's really difficult to actually understand all the causal mechanisms at play. The place that we're starting right now is language. And language is interesting because I think people think like human language is one structure. But I think if you look at the difference between, even when you speak the same language, written language is fundamentally different than the spoken language, is fundamentally different than emojis and things. And so these are all sort of like substrate, embeddings of a very specific kind of structure that emerged in our biosphere. So so that's the place that we're starting, is actually with language. And so, and it's a little interesting also, like the point I try to make with the molecules and atmospheres and minerals is they're all made out of atoms. And so we have a concept of a thing in the world we call atom, but those systems are really fundamentally different. They just happen to be composed out of the same kinds of parts. And so I think it'll be really interesting to apply the theory to things that we think of as being much more abstract. But the way that I would approach that personally is to start thinking about those things as physical systems and really try to ask questions about the physicality of its embedding. And I think this is where it gets really interesting, because I think the representations in our mind are not the physical world, obviously. And so a lot of my intellectual exercises are saying I have this mental map, but what would be the structure underneath that map? And so this is one reason I like language, because I think most of our perception of reality is filtered through language because that's how we're communicating with each other. But I don't think language is the thing it describes. So there, which I mean, obviously all of us know. But there are some things that, you know, the other thing I just wanted, just a brief point, sorry, because I've been thinking about this a lot lately and it's super interesting, is we do develop symbolic representations in science, but we also develop them to discover new regularities about the world. But those regularities seem invariant to the symbolic representation. So like gravity, you know, was developed through Newtonian physics. It was modified through Einsteinian relativity, but we didn't forget about a concept of gravity. And we didn't radically change like the perception of the world we have about the nature of gravity. So I think there are some fundamental things that we intuitively build into our theories that become independent of the particular symbolic representation of the time they emerge. And so what I see like assembly theory being a part of, because I see this in a lot of spaces right now, is this idea that contingency and causation are really fundamental to the way that at least we interact with our universe, whether it's fundamental to the universe itself. So I think having theories that capture those regularities will be really important, and that's why I'm excited about what we're trying to do, but also what other people are doing.
Thank you very much, Sara and Carlos. We see that there are so many things to discuss. We could continue all the evening. But let us give the word to our audience. It will come certainly new views and new questions. So please, the floor is open for discussion.
If nobody has a question, I have a question. So
I have a question.
Yes.
everybody has a question.
Such a fun group. I love it.
So I'll start with a question of I think grounding importance, and this is from both presentations. I noticed, shall we say, a lot of allusions to mathematical grounding. But not really logical consequences of the mathematical grounding into forming the boundaries of epistemology and ontology. Mm-hmm. And without that, I wonder about if either of you has a clear conception of the notion of scientific notations.
Mm-hmm. Could you elaborate on what you mean a little bit more? Because I feel like you have some things in your head that I'm not really sure how to orient responding to, and I'd like to understand a little bit more about what you mean.
Well, let's then change to the language of symbolic logics. Mm-hmm. Each of the major scientific disciplines have associated with them a notation that is expressed in terms of connectivity among symbols. Mm-hmm. And this necessity for connectivity among the symbols is necessary to generate mathematical models or linguistic models or chemical models or genetic models. So that in the absence of that, I fail to understand how you're connecting epistemology to ontology.
No, I mean, of course, I would consider scientific notation as ways of describing phenomena. Let's say in a very general way, it would be different narratives, and of course, not very different from literary narratives, but at the end, it's a way of describing observations. And then the ones that turn out to be useful, let's say taking a pragmatic stance, then those will be propagated they will be used. So I would say that's the way of grounding which different of all potential descriptions favor to be used, the ones that become more useful for a specific purpose in a specific context.
So fundamentally, then you're basically following Charles Sanders Peirce's work from the notion of pragmatic logics or pragmaticism and semiotics.
Yeah, more Wittgenstein, and more recently Howard Patti here in Binghamton kind of has developed biosemiotics further. Yeah.
Thank you very much. Kate, please, it is your turn.
Oh my, it's great to see you both and hear this sort of juxtaposition Sarah, I'm really pleased to have you at work on the mechanics that are underlying reality proper. And in my own way of thinking about this, I use an agent in the machine model. So what I see you doing is really building a solid foundation for the machinery of objective empiricism. And I'm really glad you're on the task, because if anybody can do it, you can. So then I hear Carlos coming in, and he has a little bit more of the role of the agent and the role of information as a symbolic system and a meaningful thing rather than a structure or a process. So what my question for you would be, Sarah, are physicists coming to appreciate that there might be something very deep about the subjective perspective? So that's question number one, and I want to link it to the idea of a frame of reference, an interiority, kind of a subjective relativity that might be more foundational than Einsteinian relativity, where you're defining as an observer these coordinates. So that's my question for you, and also to both of you. Can we really discuss information without discussing forms themselves?
Yeah. I've been thinking about forms a lot lately. That's great. To answer your first question, I can't speak on behalf of physicists writ large, but I think physicists have grappled with the issues of subjectivity for as long as we've been doing it, right? Because the whole process of theoretical physics in particular is to try to turn the subjective into something we can say objective, within the context of knowing it's all subjective. So I don't think there's an answer there, but I think your more fundamental question, which is really interesting, is there a role for subjectivity in our fundamental understanding of the world? And I think there absolutely is. But the challenge we have as scientists is that, and this goes to the hard problem of consciousness and everything, like the subjective in a world is actually not shareable by its very definition, right? So like there are some things that are intrinsic to my cognitive architecture and the interior processing of my brain that I simply cannot put in language and share with you. And if we think about science, science is built from societies, and societies have as a substrate, one of their substrates is languages that humans generate. And science is a cultural institution. It's a societal level technology. And so when we think about science as a fundamental process, it has to be information that's shareable. And so the process of science is actually trying to turn the subjective inner world of the scientist into the objective world that's shared by societies. And so the question that you're asking is actually really fundamentally deep, like how do you maintain an intrinsic intersubjectivity in a way that actually allows, and I think that's a question we need to ask, like what kind of societal infrastructure, would it be science, or would it be science evolving in a different way that would actually accompany that? And I don't know the answer to that, but I think this is one of the things that I'm thinking a lot about, and I think it's a really hard question and a really brilliant question. So that's my short answer.
Okay.
Gordana, this is Stu. Can I
just say one really
quick Carlos has got a question, the same question. First, Carlos.
Yes.
Yes.
Yes, very quickly. I think that forms are a subset of information, even when etymologically it is the other way around, in the sense that, let's say, all forms can be described in terms of information, but not the other way around.
Okay, I just want to make one more quick comment about honoring the perceptual capacities of the living embodiment that are common across living systems. I think I put a little bit more authoritative epistemological validity on the processes of the organism than have been given in the past. The embodiment is flawed, it's biased. I think that those are misassumptions. That's all I want to say for now, but thank you both. This is fabulous.
Thank you. And Pedro was the second one with the question.
Okay, a very, very quick comment to Sara. Your schemes on how the complex molecules were built, have reminded me a chemist in the middle 90s who passed away very prematurely. He was, I think, in his PhD, and he was extraordinary because he developed an information theory on how the complexity of molecules could be measured by information theory. And the work was unfinished, and someone sent to his acquaintances his work, and I wonder whether I could find it, and maybe you could be interesting, because he was very gracious, considering, I mean, your figures have reminded me his figures, etc.
Yeah, I would love that. If you do find it, please do send it to me.
I will try, because it was before the internet.
Yeah, oh gosh.
I don't know. And I have a very naive comments in between the objective and the subjective. And it is the intersubjective. I mean, and we in science, we live in the intersubjective with very strong rules for the intersubjective organization. And I emphasize the coherence between perception and action. It is the cruise of the scientific fact. A fact is a series of observations that match with a series of actions. And then because of the enormous complexity of the world, we need to create different ways to organize the intersubjective. And we have to change the rules along the process. And this is the wonderful task of scientists. But I don't find interesting the dichotomy between, I mean, talking in scientific terms. Philosophically, yes, it can be interesting, but for me it is not very productive, very fertile discussion. And I agree much with your point, Sara, last what you have said about that.
Thank you.
Thank you. And Bill Miller, please.
A question for Sara and then a comment to Carlos. First, both of you, thank you so much for a terrific presentations. Very enjoyable. Sara, I'm a neighbor of yours.
Oh, really?
I live in Partners Valley.
Oh, wow. Oh,
Just
great.
down the block, so to speak.
That's amazing. Wow, I'll wave your way.
I saw you. The question I have for you is, you mentioned selection. As behind causal ordering. What's doing the selection?
Things that already exist.
No, that's not.
No.
The selection is different, at least in evolutionary terms.
I don't think so. I mean, I think one of the things we're trying to get at, sorry, I would love to hear what you said, but like one of the things we're trying to get at is the mechanism of selection. So I think the assumption is some of the causal mechanisms are too large in space and time to actually pin down precisely. Like if you look at a ribosome, a cell is a much larger physical structure and it's necessary for the existence of something like a ribosome. So what we're trying to say is you can actually measure the shadow of those very massively distributed constructors in the objects that they do. And that's evidence of selection. But the mechanism of selection is something quite different. So I just want to, but go ahead and tell me what you're thinking on it, because I would love to. Yeah.
I would rather hear from you how you think selection works within assembly theory. Selection, in my own terms, is simply an agent participating in a set of in a choice based on information, and with information difference that makes a difference.
Yeah.
So I'm interested in I think the self-assembly that you describe is extremely useful, but you've chosen to include the term selection, and I just really think that requires a certain definition of terms.
So I think one way of thinking about it is that there is actually, like, I don't want to use choice in an anthropocentric sense, but things that persist, like the ones that are like selected or chosen to persist, that's what we mean by selection. It's really just simply like, do you observe it or not? And if you observe it and you know that there is like a very large space of causation, then that implies that there were some choices on the actual causes that remain instantiated in a system. And as far as like the actual mechanism of it, I think about like a sort of combinatorial explosion of causation in some sense. And so you basically have this process where you start with very simple things and it combinatorially explodes into the space. And unless you have some objects, and this is where like what we call symbolism and function starts to come in. Unless you have some objects that actually recognize other objects and can causally constrain the past history that's constructing those things, they can't persist. And so the persistence actually becomes a feature of the fact that you have this causal hierarchy being built up. And, you know, there's always going to be this sort of combinatorial explosion on the fringes. And the thing that we call function is sort of an emergent feature of things actually enabling each other's persistence through time. And so obviously that's a little hand wavy and abstract right now. We're trying to actually pin down the mathematics of that mechanism. But like, I think the intuitive process that's happening there in a combinatorial exploding space and thinking that you actually can't predict all the causes ahead of time is one of the reasons I don't like function as a fundamental concept. You can post-select on function, but you can't pre-select on function, which I think Stu has been saying forever. You can't like iterate over all possible functions before they happen. So I think function is an evolving concept, but I think the causal structure underlying function is much more objective and much more universal. And that has to do with this persistence and these causal hierarchies.
Okay, thank you. A comment to Carlos, just be a second. You were asked, what are you? You said information.
That question.
I would have said, if, just as a joke, permit me, the next time you're asked, say agent, because first you are an agent, and then you construe your information about yourself, and then of course your information to another agent. So that would be my preferred answer for the next time you're challenged. Thank you.
Me too.
Gordana,
Yes, please. Stu is waiting. Yes, please.
So I have one question for you, Sara, and one for both of you. Sara, the assembly theory work is beautiful, and I'm stunned by the idea that we could apply it to atmospheres. You're doing it now. About a year and a half ago, Kate and I were at a meeting, and I can't remember the name of the person. I will, though. The idea is we could look deeper into atmospheres with improved technologies. Therefore, we could see more complete description of the molecular diversity of those atmospheres. That's not infinitely far away. I'll try to remember his name. I don't know. I'll remember it. It would lead to the possibility that we could find signatures of life just applying assembly theory to the complexity of the atmosphere. Where is that before I ask my second question?
So we're writing up the paper now. We have some white papers written for Hab Worlds on the specifications of the IR actually to get assembly index from exoplanet atmospheres, which I'm happy to share the white papers, but the actual technical paper my PhD student is working on right now, but I will certainly send it to you when we have it ready.
And when Kate, I will remember the name of this interesting guy that we met in Rio. We also went walking on back, you got to go to Rio. And my second question starts with you, Sara, but it's really to both of you and all of us, Carlos. Sara, do either of you know Robert Hazen and Mike Wong? So Robert has brought forward the idea that you kind of raised too. Do minerals show open-ended evolution? And they're defining a notion of a space of the possible. They hope to find evidence for open-ended evolution in minerals. And then they say, well, it looks like we don't have it, that there's an upper bound on the complexity of minerals. So about a year ago, they were saying, well, maybe not. Whereas I think we all think, and I think we could say why, life really is capable of open-ended evolution, and I can dilate on it. So with the framework of Bob and Michael's tried to take us into open-ended evolution in general, what do we think it takes? And that's to you, it's to all of us. Carlos, you said something that I'd just like to build on for a moment. You said something about the same word can mean different things. It's the meaning different things. It's an example, think of Wittgenstein and the use of a word, the meaning of a word is in its uses, okay? So you get Wittgensteinian language games that cannot be reduced to one another. In cells, a molecular structure, the same molecular structure can come to have different uses, therefore different functions. This emergence of different uses is somehow part of open-ended evolution. I mean, I'm persuaded of that. But what do you guys think? Where do we get open-ended evolution? So please answer it, you two. We got about 4 minutes.
I'll let Carlos go first because I feel like I've been talking a lot. I have lots to say on it, but I would like to hear what Carlos has to say too.
Yeah. So first part, I think that maybe they observe like an upper bound in the complexity of minerals because they, let's say, a further increase in complexity would require a metasystem transition like life. And then you can have life manipulating matter in more complex ways, like in particle accelerators, for example, or using Sara's example of a plastic bottle of water. If you find it in a planet, then it means that there's a highly developed civilization arose in order to be able to produce that thing that, let's say, chemically is not very complex. So I would say that one would require to start considering metasystem transitions. And I think we get open-ended evolution precisely when you have this flexibility of changing the use or the meaning or the rules of a system, because then that allows you to repurpose existing solutions. And if you don't do that, it would be like pre-specifying your state space, and then eventually you will explore it, even if it might be huge. Let's say there might be some very little corner that might have interesting, but you won't have something completely new. And if you have the possibility, let's say, of course, a state space is an abstraction and it's a simplification of the real world. But let's say if in a real phenomenon, you have the equivalent of new variables, new dimensions, then that gives you the possibility to have novel behavior and new rules and so on, and keep on increasing complexity, not necessarily upwards, but let's say variety in general.
Sara?
Yeah, I don't think minerals evolve. I think minerals are product evidence of selection. And so I think if you have agents on a planet, we're using the word agency, they can actually reshape the environment in certain ways, and things can be signatures of that. So I thought about this a lot also with the atmospheres. Originally, I was very skeptical we'd be able to detect life in the atmosphere because atmospheres are not very combinatorially deep. There's only about 16,000 molecules that could possibly be volatile. And so that doesn't really give you a large space for open-ended evolution in an atmosphere, for example. But it is possible, like after all the work that we've done, I'm pretty confident it's possible to measure the causal imprint of a diverse ecology on a planet in the atmosphere, which is what we see in the structure of the assembly space. And in fact, actually, I didn't mention it, but we have a really cool result where if you look at the atmosphere above land masses on Earth, you can see that the atmosphere above urban China is more complex than the Amazon, is more complex than the Sahara. So even on a planet, you can see the local variability of the causal imprint of selective construction on the planet. Yeah, I'm really excited about that result. Estelle Janine is leading this project. She's such a badass. I may use the technical term for what she's done. But minerals I think are quite hard because the question is, are you talking about an abstraction or the physical material? And the unit cells of minerals are a way that we describe the repeating units in a mineral, but like the physical material of a rock is quite different than this abstract representation. So the abstract representation has a limit to the complexity, but if you actually look at the physical material and the macroscopic order in the physical material, natural minerals are not very selected because they have random periodicity in the lattice of the mineral crystal. And so what you would count as like copies of selected objects has like this very varied distribution, and there's not like really a tight distribution on this macroscopic order in the material. But materials can be selected to be more complex. And so what we see with assembly theory applied to minerals is that technological materials where you have a repeat of precise ordering in a silicon chip actually have high assembly, whereas natural minerals don't, because they don't have repeated macroscopic order. And so I think there's evidence that materials can continue evolving as long as there's a selective architecture or constructor to actually causally constrain the space even more. You can see this in chemical space too, where you have a bound for abiotic systems, but I think there's also a similar bound on how complex a molecule can be, depending on the technology you have on the planet and what kind of chemical synthesis you can do. Or Carlos mentioned like the periodic table of the elements. Clearly some of them can only be made technologically. So I think open-ended evolution has to do with the substrates, like what causal substrates are available. Are, you know, language to me is a new causal substrate that only emerges after many billions of years of biological evolution, allows new possible spaces to emerge. But then also like the sort of like what constraints are available from other kinds of agential systems in the environment that can impose new constraints on a substrate. So it's really like a co-evolving ecology of different mechanisms and different substrates. And some of them will be limited for billions of years, and then suddenly something will evolve that can actually, you know, now impose a selectivity and emerge objects in high copy number and high complexity out of a substrate that wasn't possible before, which is what I think we're seeing with like people saying there's minds in our machines and everything. Like, what are we doing? The humans are the environment selecting on these systems to have a particular causal structure that emulates what humans are. So these things don't happen spontaneously. Evolution is possible.
Gordana, Gordana, can I say one more thing?
We must ask Pedro, he is the boss. Pedro, how much time we have?
I don't have to say anything, Pedro.
We have Sue, we have Eric, and Sherry.
So I'm beginning better to understand this notion of unprestatable. And I have found my way to define something I'm going to call the indefinite. I got to it because I've been saying for years the number of uses of a screwdriver is indefinite. Well, it's a really weird word, and I think I know what indefinite means. And in thinking about this in this work that I did with Andrea Rolli on a third transition in science, published, is the indefinite is the items in question have three properties. They are not listable. They cannot be ordered relative to one another, and they cannot be deduced from one another. So just hold that. Mikhail Prokopenko, about a year ago with Paul Davies, Sara, wrote a paper in which Mikhail proved that you cannot put uses of something, you know, as in Gibson's a horizontal surface affords you a place to sit. That's a use. So Mikhail has proven that you cannot put the uses of something into one-to-one correspondence with the integers. Well, that means the uses are not listable. But it's also obvious that different uses are not ordered relative to one another. I could use a screwdriver to pick my nose, or a screw and a screw, or, you know, scrape some putty. And you cannot deduce one use from the other use. This is precisely, by the way, Carlos, this repurposing. And so it's turning out that that seems to be a definition of the indefinite. Hold it for a moment. I think it's deeply related, and this is just stunning, it's deeply related to the Chinese notion of the Tao. The Tao that can be said is not the Tao. And the biosphere that can be said is not the biosphere that will come to be. The global economy that can be said now is not the global economy that will come. There's something really interesting about this notion of the indefinite. I think it's okay, you guys, I'm not sure, but if it's right, somehow or another, one's finding the Tao 3,000 years later, and Lao Tse knew it perfectly well. We're just a little slow.
I agree. I like that.
Yeah, I'm very confused by it.
Usually it's a good state of mind.
And then, thanks.
Sorry, I would need to leave like in 5 minutes to teach. I would like to stay longer, but
no, please, excuse me. Let's take the words asker, the hand raiser, and let's try to be brief in the questions and the answers. so we can finish relatively well so that Jorge can manage his things. It's okay? Is it okay?
Maybe we can listen to all the questions quickly and then to wrap up, because sometimes the questions might be related, and then we can give a shared answer.
Then we proceed with Eric first and Sherry second.
Okay, my first reaction to you, Sara, was that you're basically copying Komodoro and applying it in the way you apply it. But the other thing that I think is interesting is, have you thought about the relationship to social intentions and actually the process of developing these strings that lead to a certain process, right? So that if you look at strategically, then you have some kind of intentionality involved in the process. Anyway, so brief question.
We'll get through all the questions. I have comments, but I'll hold
Yes,
mine.
please, Sherry.
So that was great, Sara and Carlos. Sara, your assembly theory was fantastic. And I don't know whether you know that I quote you endlessly about the algorithmic takeover of biology. you and Paul Davis's quotation, I bring it up often. But this is about the old-fashioned, I wouldn't say old-fashioned, but just maybe, holding up the UK. I'm coming here from the UK, and this is Nick Lane, the biochemist at UCL, keeps endlessly, his take on life and this transition from inanimate to biology is about this thermal, the deep hydrothermal vents in our oceans and so on, right? So in that theory, he talks about Krebs cycle, which of course in computation is the famous palindromic computation, where if you need to repeat, life only needs to repeat itself, right? And you have these palindromic cycles, that's all very well, but you wouldn't have complexification, because there you need some various advanced sort of computation coming in. So I just want to take your view on, there was this famous, it's still very prevalent, I think, on this side of the Atlantic, about the hydrothermal vents as being the beginnings of life, partly because they think it generates this palindromic cycle that's necessary for the Krebs energy thing that finally you need for life. I'll stop there, but I have other comments.
Okay, shall we ask Krasimir to pose the last question? This is the last one.
Thank you very much. I'm very pleased to listen these two presentations, but at the end I want to return you to the concept of information. We say many things, but not so much about information. My question is very simple. Imagine terrible co-ops like nuclear war, which will kill all living creatures, flora and fauna. So, in such situation, will information and complexity exist?
Okay, now it's time to react to all questions, please.
I can start with the Krasimir's last one. Yes, it will be less complex, but then it should start increasing again. I mean, just as there was there was information before life, or let's say, yeah, and there was complexity before life.
I have two comments. One is I tend to not favor the historical origin of life. I mean, I don't think about it as much, right? So I'm not really necessarily worried with what environment on the primitive Earth life forms first emerged from. I'm much more interested in the experimental program of, can we go in the laboratory and emerge de novo life and understand the physics that underlies that process. So obviously, I think like my view is solving the latter will help with the former. But I think going into the, like dissecting early environments and trying to understand what's going on is actually like too hard a problem. And it's actually easier to think about the experimental program of combinatorial spaces that planets might generate, and how do you actually build experimental systems that don't put selection and agency into the system, and you look how much selection and agency can emerge out of a chemical system, and how do you measure it. So that's sort of the way I think that. And as far as the distinction between assembly theory and conglomerate complexity, I'm really confused that people think they're the same. I mean, I understand on sort of a minimum description length, but description length is not what assembly theory is about. So the ontology is fundamentally different. And so I'm happy to have a longer conversation about it, but I don't understand where the relationship is at a fundamental level.
Okay, let's stop.
Comments on Sherry's question? So.
I think Sarah answered it. She said she's not particularly worried about what conditions in early Earth created life, right? No. I mean, that's true, but I mean, it certainly didn't. It came, whether it came from geothermal vents or not. One really doesn't know. But the conditions, they say that the chemical conditions. I mean, this is Nick Lane's whole thrust. I mean, which does feed into the idea that simple life could have started there. I mean, just because of the regularity of the way in which these vents behave. But who's to know? The mystery created that after that hypothesis, right? Life hasn't been created in a test tube or in any lab, as far as I know. So there's still the jury's still out on that. Yeah.
Thank you very much. Thank you very much for great discussions, for so many questions. I have a list of my own. I cannot ask you, but I hope that Sara will join. We have a group list where we discuss those questions. Carlos was already a guest with his lecture on the topic of limits of formal systems, and we might invite Sara to give us more reasons to discuss together. So thank you so much. It was so exciting.
Thank you.
Thank you. Bye.
Bye.
Bye.